Okay, hello everyone, and welcome to ME304 Machine Design. We're doing a problem with the stress analysis in the teeth of a gear. We have a spur pinion, which is milled. You have to pay attention to this. These properties of the gear are all things that will be used in here in a minute. 17 teeth, 1.5, a module of 1.5, and it's to transmit this much power with a speed of 400 RPM. So find the required face width and see if it meets the normal requirements for face width, and I'll show you that inequality here in a minute. And then determine if the resulting face width meets the general rule, which we have at. Okay, so just getting right into this, finding the face width. Whenever you're doing a stress analysis for a gear, figuring out how strong it has to be to meet certain requirements, you always use the Lewis equation, which is sigma kV Wt all over F times the module times the Lewis factor. This F is face width. It is not a force. This is a really tough thing to remember because you're used to using force, F for force and everything before this, but this F is the face width that we're actually trying to find. Wt is a tangential force. V, excuse me, V is another one of those, kV is the velocity factor for the Lewis equation based on how the gear is made. And then we have the module and the Lewis factor, which is based on how many teeth you have in the gear. Okay, so we're going to rearrange this a little bit. So we're going to try to find force, kV, Wt. I'm going to put the T up in the exponent here, just to separate a little more. That's the Lewis factor. And the reason I'm doing this is because we can get the maximum stress that it can take by using the yield strength that it has all over the factor of safety. And so that's why we're rearranging this, because we want to find out what the maximum, what the face width is. So we rearrange this equation to get face width, and we can find the stress from this, maximum allowed. Okay, so now, for a milled gear, you have to look in the tables. I'm sorry, my throat is a little dry. kV is going to equal 6.1 plus the velocity of the gear, 6.1 over 6.1. V is in meters per second. The tough part about gears is always making sure your units stay straight. So make sure that V, the velocity, the straight velocity of the gear, you got it, it's this velocity, is equal to meters per second. So in order to get V, you use pi times D times the rotational rate. I'm going to change this N to Fs up here so you're not confused. This N is RPM, and then the diameter, and then pi. And diameter you can get from the number of teeth on the gear times the module, which is equal to 17 times 1.5. So D is equal to 25.5 millimeters. And then that means V, V is equal to pi times 25.5 times 10 to the negative third meters. So we keep it in meters per second because remember that's what we're going for. Meters per second times 400 revs per minute. And then we need it in seconds, so 1 minute to 60 seconds. And there is our conversion, which is equal to 0.534 meters per second. Now we put this back up here into the kV equation. And kV for a milled system is going to equal 6.1 plus 0.534 all over 6.1, which is equal to 1.088 meters per second. Well, technically. This is actually, you don't have to have units on this, but it is technically meters per second for this constant, but it's not a big deal right here. Okay, so now we need to find what a Wt is, what the force is. So we have the power that's being put into this thing, so we can just use the equation Wt is equal to h all over pi dn. Alrighty, and as you can see, that's W pi dn is basically just the V that we found up here a minute ago, but I'll recalculate it anyway just to make sure that we have the right units again, which is equal to 0.25 times 10 to the third Newton meters per second kilowatts, basically, all over pi times 25.5 times 10 to the negative third, all over 400 revs per minute. And then 1 minute to 60 seconds. And again, I restate that this is just V. So WT is equal to H over V, basically in this situation. So all this is going to go to 0.534, which is this value up here. And then if you solve that out, WT is equal to 468 newtons. Alrighty then. So then, I'm going to go ahead and get a new sheet of paper. So from table A20 now, we're able to find that SY is equal to 220 for the material that we're using for this steel. So then sigma allowable is going to be equal to 180, wait a second, 220, 180 over 2.5. Well, that's odd. I think my professor made a mistake here somewhere. Let me do a quick calculation. The notes he gave me divided by 2.5. Okay, I think this value, SY, if you look at the tables, use whatever value it is, but this is SY right here. So this should be 180. He wrote down 220 in his notes. But 180 all over 25, or 2.5, which is going to equal 72 megapascals. Alrighty, so 180 megapascals all over 2.5. Okay. So this is 180, this is 180. The 220 is the incorrect number there. And you use 180 in this equation, so we're going to go ahead and run with that. Okay, and then from table 14.2, oh, if you're not aware, we use the Shigley book, Shigley Mechanical Engineering book, so all these tables are from this book. Alrighty then, so 14.2, with 17 teeth, the gear is going to have a Lewis factor equal to 0.303. Alrighty then. So now we have Lewis factor, we have WT, and we have KB. We can go ahead and solve for face width now. Then my pencil is dry. Okay. So face width is equal to, using this equation right here that we defined earlier, face width is equal to 1.088 KB times 468 newtons over WT times 72 times 10 to the 6 newtons per meter squared times 1.5 times 10 to the negative third meters times 0.303. Okay, which is equal to 15.6 times 10 to the negative 3 meters. And of course you can turn that into millimeters, which is equal to 15.6 millimeters. So 1.8 is the equation we used earlier with all the calculations. Equals 15.6 meters times 10 to the negative third, which is equal to 15.6 millimeters. Alright, so that's our face width. Depending on how your professor wants it, he should be fine with that because that's still scientifically accurate. Alrighty then, so now there's one quick little thing we have to do with this. You don't ever really want a fractional face width, so you always round up. So the face width is going to equal, you have to round up even if it's 15.1, because if you made it 15, then that gear might actually be weaker than the setup that you want, the constraints that you have. So you round this up to face width of 16, and that is actually your answer. So that's a partial answer, and your professor might allow that, but he probably shouldn't. In my class, we have to round up to 16. Okay, so now, find out if this meets the rule. So we need to find the circular pitch diameter, which is pi times the module. And if you do that, that's going to equal 4.71, using the module that was defined in the problem. And then you have to meet the criteria of face width being less than 5 module greater than 3 times the circular pitch diameter. Pitch diameter, right there. So then, if you do this calculation with the pitch diameter that we have defined up here, you've got 14.1, and F is obviously equal to 16, and this 5P is equal to 26.3, so it meets the rule. That is an appropriate face width. And that is how you do a face width analysis based on stress for a gear.